the previous lesson, we exhibited that the graphs of certain functions help us to find the maximum value and the minimum value of those functions. For example, from the graph of f of x is equal to 2x squared, it can be easily deduced that the value of the function f at point 0 is 0, and that the value of the function is always greater than or equal to 0 for all real values of x. This means that the minimum value of the function is 0, and the point of minimum value of f is x is equal to 0. Also, there is no maximum value for this function, since the value of the function increases as x increases from 0, and also the value of the function increases as x decreases from 0. In addition to this method, there is another method known as the first derivative test, which is quite frequently used to find the minimum or maximum value of a function. Let's learn about this method step by step in detail and find the local maxima and the local minima of the function f of x is equal to 2x squared. The first step is to find the derivative of the function f of x. The derivative of the function f of x with respect to x is equal to 4x. After finding the derivative, we equate it to 0 and solve it for the roots of f dash x equal to 0. On equating the derivative to 0, we get only one root, and that is x is equal to 0. The roots so obtained are known as the critical points or stationary points of x. At these critical points, we find the local maxima or local minima of the function f by observing the behavior of the function in their small neighborhood. If the derivative of f is positive at the left neighborhood values of a1, and if the derivative of f is negative at the right neighborhood values of a1, then x is equal to a1 is the point of local maxima. Similarly, if the derivative of f is negative at the left neighborhood values of a1, and if the derivative of f is positive at the right neighborhood values of a1, then x is equal to a1 is the point of local minima. Let's now get back to the problem. In this case, there is only one critical or stationary point. Let us now observe the behavior of the function in a small neighborhood of 0. The sign of the derivative of function f is negative when the value of x is slightly less than 0. Also, the sign of the derivative of function f is positive when the value of x is slightly more than 0. It means that the derivative of the function f changes its sign from negative to positive when x increases from the left neighborhood of 0 to the right neighborhood of 0. Hence, we can say that x is equal to 0 is the point of local minima. This discussion leads us to the mathematical definition of local minima and local maxima. Let f be a function defined on an open interval d. Let f be continuous at a critical point a in d. Then, if the derivative of f changes its sign from negative to positive as x increases through point a, then a is the point of local minima. Here, the local minimum value of the function is its value at a. If the derivative of f changes sign from positive to negative as x increases through point a, then a is known as the point of local maxima. Here, the local maximum value of the function is its value at a. Now, take a look at this graph. In the diagram, the tangent line is horizontal at 0, 1, and the slope of the curve is 0 on both sides of this point. That is, f dash x does not change its sign as x increases from the left neighborhood of 0 to the right neighborhood of 0. So in this case, 0 is neither a point of local maxima nor a point of local minima. Such a point, which is neither a point of local maxima nor a point of local minima, is known as the point of inflection. Mathematically, if the derivative of x does not change its sign as x increases through a, then a is neither a point of local maxima nor a point of local minima. Such a point is called the point of inflection. Now, let us take a quick look at the steps to be followed to find the local maxima or minima using the first derivative test. Let us now geometrically define local maxima and local minima with the help of graphs using the first derivative test. This figure shows the graph of a continuous function f defined on an open interval I. Let a be any critical point in I. Here, we can observe that the derivative of f is negative at every point sufficiently close to and to the left of a. Similarly, the derivative of f is positive at every point sufficiently close to and to the right of a. That is, the derivative of f changes its sign from negative to positive when x increases through a. In such situations, point A is known as the point of local minima. Now, let us look at another figure. This is the figure of a continuous function f defined on an open interval I. Let a be a critical point in open interval I. As per the figure, the derivative of f changes its sign from positive to negative when x increases through a. That is, the derivative of f is positive at every point sufficiently close to and to the left of a. Similarly, the derivative of f is negative at every point sufficiently close to and to the right of a. In such situations, point A is known as the point of local maxima.